All right, I think we should get it started, Puria, right?
Thank you,
Um,
Doctor.
so basically, yeah, this is the well, in a series of Voice Grid Academy. We have a presentation today. I'm here with Puria. I'm Ali Naderian, technology advisor and a partner at Voice Grid Energy. And here we have the webinar, a review of online condition monitoring techniques for induction motors. Good morning, afternoon, evening to all who are attending now. And so this is a very exciting one. And I let Puria to introduce himself and start it. WiseGrid not only offers technical consulting and test equipment and also design software to the industry, but through the series of webinars and the Academy of WiseGrid offering, basically discussions on different technical topics, and this is one of them. So thank you all for joining, and without further delaying this, I let Puria to get it started, and go ahead, please.
Thank you, Dr. Naderian. Hello, everyone. My name is Puri Karami, and I am an application engineer in Vice Grid Energy. In this session, we will review the basic of condition monitoring of electrical motor, a brief introduction to MCM1 device. I hope we have enough time to have, and let's get started. Okay, one of the main goals of motor condition monitoring is to prevent unexpected shutdown and reduce maintenance cost and downtime. Fortunately, in most cases, motor failure doesn't occur suddenly. They typically start as a small defect which grow over time and eventually cause a trip or complete failure. As you can see in this slide, when a fault begins to develop, we can detect it by analyzing a various signal from the motor, for example, oil or a current signature or vibration goes up, and at last the complete failure happens. So the sooner the fault is detected, the less severe the damage will be and the cost will be less down the failure. So this diagram shown here is known as a PF curve called prevention failure curve, and it illustrates the dependence of monitoring views and a motor fault can be detected time. So in the following slide, I will give you an advantage and disadvantage of every method called here. Before we move further, let's take a look at some statistics on the motor failures. According to the studies conducted by EPRI and IEEE, around 50% of motor failures are related to bearings. However, other components such as stator and rotors cause a major portion of failures. This fault can be caused by a variety of factors such as external conditions such as abnormal loads or poor power quality of the electrical system, or human factor can affect the faults. For example, improper bearing lubrication or frequent motor start can lead the heating of the rotor and stator. But in some cases, the issues are unavoidable. For example, due to poor material quality in the manufacture, or the presence of the moisture or the contamination we have in the environment. So therefore, it is essential to continuously monitor the condition of the electrical motor and identify the hidden or developing fault before they cause a failure. Now, let's take a closer look at the different parts of the electric motor. As you can see here, any electrical motor is you can see we have the stator or the rotor and the bearings part, the cooling fan, which will be have an introduction of every part. For example, consider the stator core. The stator core is not a solid block of the iron, but it is built from the thin sheet of high-grade and low-loss silicon steel called lamination. These lamination prevent the eddy current flow into the stator and make the when we actually when we use them to we place them together, we make the stator core. Then we have the stator windings or coils, which have the copper conductors, and the stator frame we have. Now, if you want to have a winding or coil, we need the slot insulation, we need the coil windings, and the uh, phase separation into the windings. Now, in the second part, we have the rotor. The rotor is also consists of the rotor cores and rotor bars, which will be introduced in the next slide. And each rotor bar will be short-circuited through the end rings. As you can see here, the rotor the rotor shaft uses the bearing to smooth and less uh, excuse me a little bit. And we have the bearings and the cooling system here. You can see if the fan in the cooling system is damaged or the bearings have the alignment issue, we can see the heat goes up into the system. So we need to ensure the proper cooling and uh, every time inspection of the motor. So let's summarize what we have seen here. An electric motor can fail due to mechanical or electrical or thermal causes, and each section of the motor, for example, a stator or the rotor or the bearing parts, can experience a different types of the faults, which you can see here. To maintain the reliability and having the motor condition in a healthy and good mode, we need to monitor the multiple parameters of the motor over the time. Uh, by applying the condition monitoring, we can identify and detect the developing issue early and schedule maintenance only when it is necessary and reduce the unplanned downtime and trip. The goal of condition monitoring is to detect these early stage changes. Generally, the motor diagnostic methods can be categorized in two groups, the offline methods and the online methods. In offline methods, we mean the motor should be disconnected from the circuit, electrical circuit, and a specific test condition applied to the motor. For example, if we want to assess the condition of the stator insulation, uh, we need the test like insulation resistance or dissipation factor called tangent delta. Or to check the integrity of the stator winding, we need to apply a test called winding resistance test and compare it with the period result to ensure the windings are in a healthy position. But while the most common offline test needs to be offline situation, for example, disconnect the electric motor from the circuit, or for example, detach the load from the motor. There are some other tests called the online test. And we have in the offline test, as you can see here, we have the LC test or electromagnetic core imperfection test. This test is for detecting interlaminar faults in the stator core. Or, for example, polarization index test, which is the specialized form of the insulation test. It involves taking two readings, the insulation resistance after 1 minute and after 10 minutes. The polarization index is the ratio of these two values. A healthy insulation system will show an increasing resistance over the time, and the insulation material insulation material polarized. For example, a low PI value, typically below the 2 or 2.5, is a strong indicator of the high moisture or excessive contamination inside the insulation system. However, these offline tests are not always feasible as they require the motor be disconnected from the circuit or taken offline and applied specific test condition. Many motor condition monitoring systems are online. For example, thermographic or thermovision analysis or shock pulse or as you can see here, the temperature measurement of the system. For example, consider the thermovision analysis. This non-contact method uses the infrared camera to capture the motor surface temperature profile. It is a powerful tool for quickly identifying hotspot to indicate the potential problem of the motor. These hotspots can be linked to the several faults. For example, in an overload bearing or insufficient lubrication or airflow obstruction or cooling system failure in the fans and the fins of the stator core. So thermography provides an immediate visual confirmation of the thermal anomalies in the stator, and it is ideal for rapid initial screening for the temperature. However, for a high voltage motor and medium voltage motor, we have a test called partial discharge monitoring. The partial discharge are a localized dielectric breakdown in the insulation system. However, they do not completely bridge the gap between the conductor and the stator core. PD monitoring is especially for the medium and high voltage motor where the insulation failure can cause through the insulation phase. These micro discharges can be detected by online PD monitoring, and the high frequency voltage and current pulses emitted will be measured and providing a leading indicator of the insulation degradation. Or, for example, consider the chemical analysis of the bearing grease or called oil analysis. This method involves the periodically extracting the sample of the bearing grease or journal oils for laboratory analysis. This chemical contact can reveal several fault conditions, for example, identifying the metal particles or detecting ingress of water, dirt, or process chemical or lubrication degradation. We can also see the changes in the viscosity of the oil or the grease used in the bearing. These analyses provide direct evidence of the physical and chemical changes in the bearing system. However, in this method, the motor remains operational. The fault can be diagnosed by sampling various signals such as current, vibration, temperature, or the oil samples, and have you whatever you can see here. Each method has its own advantage and disadvantage. For example, you can measure the condition of the motor consequently, but no single method can detect all motor fault. It is the combination of these methods can provide the fully inspection of the motor and condition. However, we can categorize the maintenance method into these four categories. For example, corrective maintenance or time-based maintenance or condition-based monitoring and predictive maintenance. Let's start with the corrective maintenance, often called the run to failure. In this approach, maintenance is only performed only after a failure occurs or when the asset performance doesn't been acceptable. It is essentially an unplanned intervention. The goal is to simplify the normal, restore the normal operation of the motor. We can see these methods by consider the timing, the cost, and the risk. For example, the timing, this strategy is the completely unplanned because it begins when the fault happens or something fails. As a result, the downtime is unavoidable and production often stops and needs the repair to be maintained. Second of all, the cost. This method, because this is unplanned, the costs are usually high. Emergency callouts and shipping for spare parts, overtime labors can drive the expenses up. Since we repair the failure after the complete fail or the damage tend to be more severe and the cost will be high. And the third, the risk of this method, this approach carries a significant risk than the most bad condition monitoring system. Sudden breakdowns or cause the secondary damage to the nearby components or threatening the personal safety and environmental incidents is the causes of this high risk. For this reason, the corrective maintenance is suitably only for the low cost or non-critical equipment where the expense of monitoring or preventive action usually outweigh the cost of the repair. So let's take a look at the next strategy, the time-based maintenance, simply called TBM. This strategy is more structured maintenance actions only at the fixed intervals of the time, for example, every 6 months or every 5,000 hours of working of the motor. The goal of this method is to replace and or service the components before they statistically expected to fail. And this method brings order and predictability, reducing the chaos and give us a, a little limitation in the failure. But the main drawback of this method is its accuracy. TBM is based on average data, average lifetime of the uh, asset. For example, the manufacture mean time before the failure. Rather than the actual condition of the asset. For example, consider a part, it is working, but it is replaced too early, even when they have a suitable lifetime remaining. This leads to over maintenance and waste the time, labor and materials. Replacing parts too often can even introduce new problems. Many early life failure, known as infant mortality, occur shortly after maintenance due to installation error or defects in the new parts. So while TBM, the time-based monitoring, improves the predictability compared to the reactive maintenance, it's still lack of precision, and it doesn't consider the true and real-time condition of the equipment or its parts. The next method called CBM or condition-based monitoring. Instead of maintaining the equipment at the fixed time, CBM intervenes only on the actual health or the performance of the asset. The concept is too simple. Most equipment faults develop gradually, as we talked first. If we detect those early warning signs, we can act before the failure happens. For example, CBM use sensors and diagnostic tool to track the parameter like vibration or temperature or the current signature. By analyzing this data, we can identify the potential problem in their earlier stages and plan the maintenance at the most convenient and cost-effective moment. This approach transforms maintenance from reactive to the predictive. It has uncertainty of the diagnosis into the measurable information. The maintenance team, they no longer guess or reacts. They make an informed decision based on the evidence or the actual status of the motor. So CBM tells us what is happening and how severe the fault is, but it is not enough. The next method we call predictive maintenance or PDM is the most advanced form of the maintenance method. Where the CBM detects the existing problem, the PDM steps forward. It can tell us what happens next or how much time we have before the motor fails. Simply, PDM uses the data gathered from the CBM, such as vibration analysis or current signature analysis or temperature, and apply the analytics to estimate how much time we have and how much useful life remains. So simply we can say CBM answer the question what is going on, and the PDM answer when the device will be fail. Or PDM allows us to schedule just-in-time maintenance and work exactly when it's needed. It also helps us the inventory management, it improves the risk management, and we can keeping the asset in service safely until the next scheduled shutdown. And predictive maintenance combines the diagnostic capability of the CBM and forecasting. So now let's take a closer look at the rotor inside the electrical motor. Usually the rotor have the main three parts: the shaft, the stator, the rotor core, and the bars, as you can see here. The rotor core, just like the stator, is made of the stack laminated steel sheets. They help us to reduce the eddy current losses and improves the magnetic field. And inside the rotor slots, you can see the bars. If a broken bar fault happens, it start, for example, with a little crack in one of these bars. These cracks are usually caused by thermal or mechanical stresses, which have three main reasons. First of all, the thermal stress on the frequent start. Every time that motor will be get started, the motor have a large inrush and starting current. This causes the rotor bar to heat up, expand rapidly. But if the motor is started and then get run, it will be get cooled. So this um, even if, especially under the high inertial loads, it's repeated and the heating and cooling cycle will cause the bars to crack. The second is overload or the load fluctuation. Running the motor under a sustained overload generates extra heat in the rotor bar and which adds the mechanical stress between the bars and the stator core. And the third is the manufacturing defect. For example, the imperfection in the uh, manufacturing procedure, in like blowholes in the rotor bars or the voids. This is especially common in die-cast rotor type. In these points are often very weak in the thermal and can get the crack start in these points. As you can see here, we have some example of a broken rotor bar. The damage can be minor or partial, or be the whole end ring can be detected. And if one rotor bar breaks, you can see the current was supposed to flow through this, has to find another path. It flows into the neighboring bar and adjacent bar, and the current density in this area and cause the localized heating, and the extra heat puts additional stress on the adjacent bar, which accelerate further cracking. So what starts as a small and single fall can quickly become a progressive problem affecting all the rotor performance. So here you can see in the current signature form of the stator, theoretical analysis shows that the broken rotor bar can create two characteristic sideband in the current frequency spectrum. The device is used here called MCM bar, uses a motor current signature analysis or called MCSA, sampling the current and observing its frequency spectrum around the fundamental power frequency. This figure shows a motor. This motor under the test have a you know, the broken rotor bar fall inside itself on the peak side on the around the fundamental power frequency. Another common motor fault is air gap eccentricity. This figure shown here is illustrate an exaggerated air gap asymmetry. The eccentricity can be static. The middle picture, as you can see, means the air gap remains consistently smaller on the one side and the greater on the opposite side. But in the dynamic eccentricity, the point of the minimum air gap rotates as the motor turns. So air gap asymmetry leads to unequal magnetic pull between the rotor and the stator. It is stronger in the side which the air gap is reduced and the weaker on the opposite sides. This magnetic pull variation causes the torque ripple and increased vibration, which places the extra stress on the other components such as bearings or housing of the bearing, reducing these operational lifetime. And during the motor startup, when the current is very high, the magnetic pull in the case of the severe eccentricity can be so great that cause the rotor and stator to physically rub each other. This rubbing between the rotor and stator can be so severe in the motor damage, require the costly and time-consuming repair in the stator core changing and rewinding the electric motor. So it is important to note that the manufacturing tolerances, all motors have some minor degree of the air gap eccentricity, but the MCM1 device, which will be introduced in the next slides, allows us to trend the increase of this asymmetry over the time. As you can see here, Just like the broken rotor bar fault, theoretical calculation and analysis shows that the air gap eccentricity can generate a characteristic component in the motor current frequency. These frequencies depend on the motor type and condition and varies from the motor to motor. In this case study, the current sampling using the MCM1 device successfully diagnosed the air gap eccentricity fault in the tested motor shown here. There are two sets of characteristic frequencies here. Let me enable the laser. These three frequencies, the middle one shows the static growth in eccentricity, and the side frequencies, this one, also shows the dynamic eccentricity, air gap eccentricity in the motor. The next fault can be detected in the motor is mechanical fault like mass imbalance. This fault can originate from the rotor itself or the attached load or the fans. This fault primarily generates vibration and can be detected by measuring the motor vibration. However, many mechanical faults in the motor can increase the vibration, so it's crucial to use some methods to detect the difference of the type of the fault in the motor. As you can see here, in this case, by analyzing the current of the electric motor, we have two components in the frequency spectrum. These frequencies can indicate the presence of the mass imbalance in the motor. Uh, As we talked before, this condition can be observed in the vibration frequency spectrum. It is important to remember that this component is always present in the motor vibration spectrum, but the imbalance causes its amplitude to increase significantly. Therefore, for detecting this fault, we need to comparing the current test result with the historical data and period test of the electric motor to detect the mass imbalance in the motor. The next and one of the most critical section of the motor are the bearings, usually the most common source of the motor failure. A bearing is made of several components. It can be shown here: the outer race, the inner race, the ball, and the cage or the retainer. Consider the red dot in the rotating element have a minor defection or crack. Every time that the rolling elements cross the inner race or the outer race, it generates a vibration pulse around the every time it passes through the inner race or outer race. So, and the frequency of this pulse can be detected. It is not random. It's directly related to the motor speed and the bearing dimension and specification. By knowing the operating speed of the motor, we can calculate the characteristic frequencies of these elements called BPF or BPFI or BPO, the inner race, the outer race, or the cage. So by analyzing the vibration spectrum, we can pinpoint that which part is actually is faulty in the bearing. To make this process easier, we can calculate all the bearing frequency uses its bearing codes. By selecting the correct code of the bearing, you can detect the characteristic frequencies, scan the vibration frequency spectrum for these unusual increase in the amplitude of these frequencies. Here you can see the bearing damage of the electric motor used the vibration measurement with the MCM1 device. It is important to understand the bearing failure usually develop in the multiple stage. Often the first sign of the trouble is caused by improper lubrication. If this issue is not addressed early or we don't left unchecked, the fault will progress over time and get worse. And also it can affect the other motor components such as bearing housing or other part of the motor like the shaft of the rotor. We can also use the vibration measurement to diagnose the looseness between the component in the motor foot, or the foundation, or the winding and the stator core. The core logic of this diagnosis relies on measuring the vibration, such as detecting a mass imbalance in the motor. And from the frequency spectrum, we can, according to the law of the physics, we can detect which faults are happening in the motor. The next fault can be detected in that can be happen in induction motor relates to the stator winding. As discussed earlier, every motor has the stator core and the windings. The windings are the conductors which will be placed in the stator slot, and the insulation between the stator core and the windings can be applied inside the stator core. This insulation is designed to tolerate the maximum temperature. However, for many reasons, this insulation can fail and lead to a short circuit between the conductor to conductor, or the conductor to the stator core, which will call them phase to ground or phase to phase fault. When this fault can occur, a very high current typically flows over the windings, result in a complete burnout and severe damage to the winding. We need to full replacement of the winding, and this fault can be detected by the protection relay in the substation. But many faults can occur between the turns of the same core. We call them turn-to-turn fault. In this case, the current increase is not so much high, can be detected by the upstream protection relay. But if we can detect them early, we can prevent the excessive temperature rise and avoid the damage to the entire core. To detecting the turn-to-turn fault, just like the last method we used, we can analyze the motor current signature and motor current frequency spectrum. The growth in the specific frequencies in the current spectrum can indicate the presence of the stator faults and turn-to-turn fault in the winding. And also, in many cases, we need to rewind the motor due to various reasons. In this situation, the new winding which applied can be but might not be correctly inserted to the stator slot, or the new winding specification might differ from the original winding. For example, we can use the current imbalance or the harmonic of the current to detect these issues. The next fault can be detected and happen in the motor is misalignment. The misalignment is not always visible, but it creates a significant stress on the system. We can categorize the misalignment in two type: the parallel and the angular. The parallel, the right picture you can see here, can occur when the center line shaft of the motor and the load are separated by a radial distance. But in the angular type, they have intersection points, but they form an angle between the center line of the rotor and the motor and attached load. Misalignment generate high cyclic stress on the motor and the coupling. So by measuring the vibration, we can also detect the alignment issue in the motor. Practical rule for diagnosing the misalignment: we can measure the vibration and see the frequency spectrum. Usually, the misalignment causes the 2x component, or the 2 times running speed frequency, go very high. Uh, and if the misalignment is so severe, the 3x and the 4x also rises. By sampling and analyzing the vibration spectrum, we can quickly detect these misalignment issues. In this case, you can see the 2x amplitude here, this one. This is the 1x or 1 times running speed. This is 2x or 2x running, 2 times running speed, and this is the 3x or 3 times running speed of the vibration in the motor. Uh, you can see here the 2x grows significantly high, the indication of the alignment problem in the motor. For example, in this observed case, the motor has an alignment issue, but unfortunately, they didn't shut down the motor, and shortly afterward, the motor caused a severe increase in the vibration and lead to an unplanned trip. So, and the reason was the value of the vibration doesn't exceeded the standard value, so they keep running the motor. So this is we need to have attention to the vibration spectrum. It detects the early fault stages uh, via the magnitude measurement. So all the motor faults leave a distinct signature in the current or vibration or temperature. For example, the bearing faults or the mass imbalance can be detected with the vibration analysis, but on the other hand, some electrical faults such as broken rotor bar faults can be detected in current signature. So this is important to be used. A method can not only the single one method. So in the MCM1 device, which will be designed to perform both vibration analysis and current signature analysis at the same time, by combining these two methods, we can detect a much wider range of the fault. However, some faults like unbalancy or A-gap eccentricity can be detected both with vibration and current signature. So when we have these two combined data, it can provide us confidence in detecting the fault in the motor and reduce the chance of the misdiagnosis. The device which will be described here called the MCM1 or the motor condition monitoring system that diagnose the motor fault by analyzing both current and vibration. This device is equipped with three current measurement inputs and three voltage measurement inputs and can simultaneously sample the voltage and current and also two vibration sensor input for vibration analysis. And this device is battery operated, make it easy for on-site measurement and analysis. Called the analysis, all the analysis we call is performed inside the device, and the device generates a PDF report from the record of the measured parameters. The internal algorithm in this analysis compare the collected data with the standards and the threshold and estimate the probability of the various motor faults we discussed before. In addition, the MCM1 can create a database for every motor and allows us to track the motor condition over time and let us compare the current measurement with the historical data and the period test attended to the motor. And this device provides a long range of the diagnosis tool, which will be seen in the following slides. As you can see here, this device can measure up to 1000 amp and 500 volts of the voltage and current measurement. It can be directly measured from the motor or from the sampled from the CT or PT. This device has the accuracy of 1%, and each sensor can have a frequency range of 5 to 10 kilohertz, as you can see here. Also, for vibration, the MCM1 provides two sensor input for the vibration measurement, and these sensors attach directly to the motor casing using the magnet and measure the vibration acceleration. Uh, and the frequency response of these two sensors are also from 5 hertz to 10 kilohertz, which give us a full spectrum of the motor vibration frequency and identify the low frequency mechanical issues such as unbalancy or the high frequency faults such as bearing or air gap. Also, one of the key features of the MCM1 device is to ability to online display of the measured value By observing the time domain of the measured signal, such as current or voltage or vibration, we can have a general information such as amplitude, the frequency, or the shape of the signal. The MCM1 can sample up to 32 kilohertz for over 100 seconds, which allows us the accurate frequency spectrum of the signal from 0 hertz to also 10 kilohertz of the sensor range. We can also capture the data through the motor startup to measure some parameter like starting current amplitude or the starting time of the motor. And also you can see here the MCM1 allows us to analyze the signal frequency domain. As you can see here, there is a current and vibration signal measured in the frequency spectrum, allows us to detect some faults, and by measuring some characteristic frequencies, like as the sideband around the fundamental frequency, we can detect some of the faults in the motor, just like rotor bar broken or the mass imbalance in the motor. It can also, because of the measuring simultaneous of the voltage and current, we can also a power quality parameter such as THD, the power factor, the frequency, the sequence of the voltage and current, such as positive sequence, the negative sequence, and the power such as active power or the reactive power and power factor. This device can generate a PDF report based on the power qualities and offers us a better quality power quality status. For example, some standards like NEMA mandate the motor input voltage, magnitude, the frequency, and the imbalance in the voltage input. If these values exceed the acceptable limit, the motor capacity must be derated or the motor should be turned off and tripped. For example, if the input voltage dropped by more than 10% of the nominal value, the motor should not be operated at all, or even if the motor has over voltage, it causes the increase in the stator core loss and exceed the heat in the motor. Or for example, if you have an unbalance in the motor voltage over the 2%, the motor must be derated and we cannot use the nominal power of the motor. So as you can see here, a crucial aspect of the motor condition analysis is the trending in the changes of the measured parameter over time. For example, for detecting mass imbalance, as we talked before, a key indicator was the growth of the motor vibration amplitude over time. So the MCM1 device can allow you to create a database for every motor you have in your site and record the vibration samples and comparing it with the previous data and historical data of the motor. Uh, Also, some faults like bearing fault heavily relies on bearing specifications. So, for this reason, the MCM1 has a library for all the bearing codes to detect the bearing faults only with the frequency characteristic of each bearing. Another key capability of the MCM1 is to analyze the measured signal and give us a report uh, for the condition of the motor. This report, as you can see here, includes all the necessary information. For example, frequency spectrum, the harmonic, the peak, the RMS value, and such a relevant parameter to for example, provide the status of the motor. You can use this measurement, and also the internal algorithm of the MCM1 can calculate the characteristic frequencies for various faults such as broken rotor bar frequency spectrum or mass imbalance. And called the algorithm, the MCM1 has a algorithm trained on the massive volume of collected data. This device can automatically assess the motor condition and provide the percentage based of the probability of each fault we discussed. This algorithm is trained to distinguish between the status of the healthy signal and a defective signal, and offer us the initial probability of the assessment condition, while the user can have its own experience and expertise, but this algorithm give us the initial probability assessment for a quick and general overview of the motor condition. As you can see here, there is a probability percentage based probability assessment for a motor and give us the general status of the electric motor. And also the motor condition here is can be detected by various standards. For example, for detecting vibration analysis, the ISO 20816 is used in this device to provide a general categorization for the motor. Called the ISO 20816, consider a motor size with 37 kilowatt. This motor is classified in class 2. In this class, we have 4 zones, as you can see here. For example, if the vibration of the motor is less than 1.1, the motor will be fall into the zone A, which means the motor condition is normal and can operate over time. But if the vibration value of the motor exceed 7.1, the motor should not be operated at all. So in the algorithm of this device, we use these standards called before. And also the reports of the motor can be stored on the device storage and will be extracted without any external software on your device. All you need to do, the device creates a local Wi-Fi, and all you need to do is enter the IP address of the uh, device into the browser on your mobile or your laptop and extract the information from the device. And also a USB port is on the device, allows you to transfer the data via flash drive. This USB port can be uh, used for the firmware updates with the dedicated file. And according to the database we call, the MCM1 has an internal memory, can store all the motor you have. The device internal storage is around 128 gigabytes, but for example, consider you have 10 motors or 100 motors. Each test can occupy up to 60 megabyte of the storage of this device. So to remove this constraint in the storage limitation, we have a cloud database called, here you can see, you can upload your collected motor data to this server to eliminate the limitation of device internal memory. And the MCM1 device is not limited to a specific type of the motor. It can be used around the various equipment, for example, fans or pumps or conveyors. In the diverse industrial, for example, the petrochemical or the mining or power generation plants and so. Thank you, everyone. I hope this presentation was helpful. For more information, you can scan the QR code shown here to access the supplementary detail of each motor, each device we have. Thank you for your time, and I hope that this content was useful. And also, if you have any question, I would be happy to answer.
I think, yeah, that's the time for taking a few questions here too. If there's anybody who would like to add questions. Puriya, that was a great presentation here. Thank you. I mean, to begin with, I probably have a couple of questions. Maybe I start, and if you guys want to add, you can type your questions in the chat in the public on the right bottom left of your browser. If there's one, like you mentioned, Priya, about generators, so we can use MCM1 to assess like general condition of generators, like hydro generators or gas generators and so on. Do we have we used it for like a smaller generators, for example, one megawatt or 5 megawatt generators or diesel generators, for example? Can we use that?
Actually, based on the measurement input range, we can measure all types of the motor and generator. For the generator specifically, we can have a vibration analysis, and we have the frequency spectrum of the vibration in the generator, and we can measure the current of the generator, and we have some parameter like ambulancy or THDs and a power factor of the generator to assess the status of the condition of the generator. But
Generator, yeah.
but the algorithm we call usually will be used for induction motor, and that this device can detect the fault in the induction motor and give you a percentage based fault detection.
Yeah. So the analysis is a little bit different, or it's not as similar to motors, but it extracts or it records all the parameter electrical mechanical parameters you need. So that's
Yes,
good.
yes,
Yeah.
exactly.
And one another question, like basically the vibration sensors that we have, like how typically do you like install them or position them around motors, or is it like a magnet or like as acoustic sensors that usually comes with a magnet, or how do you fix them during measurement?
We use the magnetic mounting
Magnet,
type
okay,
to the
okay.
motor, and you can mount it to the end drive end side of the motor, the non-drive end side of the motor, and the load side to measure some parameter like the phase shift between two sensor to assure that you have a mass imbalance or misalignment in your motor.
Okay. So this basically MCM1, really, you don't. It's a fully online system, so you don't have to take out or de-energize the motor or generator, right? So you,
Exactly. Yes,
yeah,
exactly. You don't need to
that,
de-energize the motor, and for applying the current measurement, you have these clamps. Each clamp can be used due to the size of the motor or the measurements you want to do. For example, if you want to directly measure the current of the motor, you can use these sensors shown here, or you can measure from the output current of the CTs.
it is okay. Yeah, for probably for larger motors or generators, there's got to be some CTs perhaps to yeah. No, that this is, and the good thing is like it has both voltage and current inputs.
Yes.
Yeah. So for voltage, usually, like if you have access to the terminals of, let's say, the power panel, you can just clip or get a voltage from there directly.
Yes, exactly. And you can measure from the output of the PT to have a power quality. For
Yeah.
example, you measure the active power of the motor, the power
Yeah.
factor of the motor, and some parameter in the
So,
power quality.
so let's say, because you're saying 500 volt is the limit, so that's good for all, pretty much all low voltage. But if I have a, let's say, 5 kilowatt, 5 kV, 5,000 volt motor, then I need to use the PTs for
Yes,
that.
exactly. In the medium voltage and high voltage motor, due to safety, you have to use the signal out from the output of the PTs and potential transformers.
Mhm. Good, good, good. Um, It looks like you have one questions from Arash on the chat.
Please let me check. Usually, for the test we perform, we take the samples up to 60 second or 100 second to detect the full spectrum of the motor to observe the 0.01 hertz in resolution in the spectrum. But the broken rotor bar, as we call, will usually shown up around the fundamental frequency of the motor, around the 50 hertz. For example, broken rotor bar usually causes increase in the 49.5 or 50.5 frequency. So gathering the data around 10 second or 30 second will allows us to detect these parts.
For that's for broken rotor case.
Mhm.
I
Yes,
see.
but for a detailed and accurate frequency spectrum, it is needed to gather data more than tens of the second.
10 seconds. So, I mean, is it safe to say MCM1? Obviously, there's a lot of features on it, but yeah, like if you want a very advanced or high harmonic content measurement, then like MCM1 is not the tool. But this is like an all-in-one measurement device, and comparing the cost of it,
Exactly.
which is a fraction of probably similar tools. That's that's what you got. If you want to focus on power quality, I think you have a point. Yeah, let's talk about that as a
For
maybe last
example,
question. Yeah.
yes, yes. For example, for power quality, due to the 32 kilohertz frequency sampling frequency, this device can measure the harmonics up to 50, and the parameters in the power quality, such as THDs or the power factors, uh, or for example, measuring the starting current of the motor can be detected using this device. As you can see here, we have a MCM1 device and a power analyzer of the Fluke, which used to compare these both devices. We measured the power quality parameters, and you can say that you have both condition monitoring device and a power analyzer simultaneously. But for
Simultaneous. Yeah.
detecting for detecting a condition of the motor, you usually use the vibration and the current. But for the power quality issues, you usually use the voltage and the current.
Power quality is a bonus here to give, and it's really hard to find commercially available, tools that go beyond 50th harmonic. Like if you really want to measure over hundreds of harmonic, and then you really need the, I'm not sure what kind of tools could be available here, but no, that's good. It was really good um presentation. Thanks, Puria. And yeah, like if there's no other questions here, we like to close the session and thank you, everybody. Follow WiseGrid website to get more updates on upcoming webinars. And there's gonna be more coming in 2026 from WiseGrid. Stay tuned. Thanks, everybody.
Thank you, Dr. Naderian, and hope everyone have a good day.
Thank you.